Hello everyone. So welcome to the session 2, the lectures on introduction to topological spaces. So let me, as last time I have given a sort of motivation to you guys for topological spaces. Let me begin with an example of topological space. As I promised, I will be discussing many examples. So let me proceed with a very standard one and perhaps one of the most beautiful. Why it is beautiful? You will be observing that thing as far as we are gonna proceed in these lectures. Okay, so I assume that you guys are already equipped with sufficient knowledge of metric spaces. Let me still redefine it for you. So definition. Of what? Metric spaces. Again. So a short note on this. I think everybody, one of us knows that metric spaces, this definition is actually inspired by the physical distance, right? The properties of the distance what we study in physics. So let us begin with the formal definition. So let X be a set, okay, and D is a function. From where to where? X cross X to R. R means real numbers. Such that, number one. So I'm demanding that D should satisfy some things. So what are those things? D of xy should be bigger than or equal to 0 for every x comma y belonging to x cross x. Okay? As well as D of x comma y, if it is 0, this will imply that x is equals to y, and if x is equals to y, this will further implies that the distance is, sorry, I should not use this word, that d of xy is 0. So if you see, this is motivated from the usual distance. Distance is a quantity which is non-negative, right? And we know that if the distance between 2 points, you can think of the distance in R3 or R4 or R, whatever. If you have two equal points, of course, their distance would be 0, and if the distance is 0, the points are equal. Okay. Second. So the next thing is the d of xy should be equal to d of yx. This should also happen for every x and y in x. Either I can write x comma y in x cross x, or I can write x comma y in x, right? It is well understood. Okay. What more? It should it should satisfy something called triangular inequality. So what is that? So if you have dxy, this should be less than equal to dxz. My x and u would be same, so I will not be using both of them at same time. I mean small u and small x. Plus d of z comma y. So this should also happen for every x, y, z in x. So what you call these things, we can formally say something like that. So this is non-negativity. This is symmetricity. And this is the famous thing, triangular inequality. Now, if your D has these properties, what I'm gonna say is then what's happening? Then D is a metric. Some people also just call it distance. Why? Because these things are motivated from the usual physical distance. But in mathematics, what we call it? A metric on X. So there can be many metric on X, right? And XD, a metric space. This pair or this two tuple, a metric space. Very nice. Let me give you just one example of it. I am not gonna verify it. I left it for you guys to do. So example, let us call it 1. Let X be a non-empty set. Someone may ask why I haven't mentioned X to be non-empty here. It's fine, you can mention it. Because if X is empty, you see, these things will become triviality because there is nothing in that set. There is no point in that set. Right? So you can mention in definition. What you can write here also, you can write X is non-empty. Good. Now, let us define a map. This I want to define like dxy is 1 or 0. Let us see when 1, when 0. When x is different from y, this is when x is equals to y. So this space you call as discrete metric space. Now, one might think, why discrete? Discrete is an English word, right? So I will be giving later on the reasons behind calling this metric space to be a discrete metric space. So like we say, a person is discrete in some sense, so it's the same thing. So we will come over it later on. Okay. Now let us proceed. Let me recall further few more things about metric spaces. I think you remember this notation. Ball centered at a point with some radius. So B, A, comma R. Let us write D here. What I mean by this, I can avoid as well as this suffix D. So what I mean is, it is collection of all x in capital X such that distance of A and X is less than R. So you call it also, if you know that, this you call it open ball. I'm assuming you guys know these things. Okay, what you call it? Open ball. Why you call it open ball? You know it if you plot it in, if you see this description. Okay, what is XD? XD is a metric space. So, why you call it an open ball? Because if you visualize this ball with the standard Euclidean matrix in R3, it looks like an open ball except the boundary. Good. Let me proceed. Open sets in a metric space. XD. Let us recall this definition. We say a set U contained in capital X. A set U contained in capital X is open if, what should be the condition? If, let me write down, for any, say some symbols, for any, say X in U, there exists, for any X in U, there exists a real number bigger than 0. Why I am writing R suffix X? Because it depends upon X as well as U. But since we have already fixed our set U and we are defining when this U would be open, so it is sufficient to write just X in suffix because it depends upon this. The point chosen, the radius, you call this radius, right? You call this thing center. So, so the radius depends upon X. How? Why I am calling this radius? You will see in a moment. Such that, of course, bigger than 0, real number. I am not mentioning that it is real number. I am just like verbally I am mentioning it. Such that, what should happen when you take the ball centered around X of radius R suffix X, this is wholly inside U, and of course this contains X. So in this situation we will call what? A set to be open. So let me proceed with my example 1. So I'm just quickly writing it since I'm assuming you guys know this fact. So for any X in X, let XD be a discrete metric space, okay? Then, for any X in capital X, if you see singleton X is actually which number less than 1 you like? Let us say 1/10. Okay? So, what it tells you, this singleton X is open in X. See, this is another way of writing. What? You write subset, down the side you write this thing, open in X. Why this is open in X? Because you can see that every ball is itself a open set, because this thing will be trivially held here. The same radius will work. Okay, so I am not going into much details because my target is to just a quick review of metric spaces. Very nice. So this is happening for every X in X. X is discrete metric space. Good. Let us proceed. Let us proceed with this thing. So whatever you want to call, you can call it a theorem. What is my theorem? Let X be a metric space. Okay, in 2 to the power x, like I told you, my tau will look like 3, okay? Sorry for that. Tau contained in 2 to the power x be a collection of all open sets in XD. That is what the definition of open set, if you just go a little bit up. We have defined with this blue color, right? So what is tau? It is the collection of all open sets, okay? Now, what is our claim? Then, let us denote this tau with tau d, okay? Because it depends upon the metric, right? If you have a metric space, you have a particular metric, and with that particular metric you have different kinds of open sets, right? So that's why tau d. Then what is my claim? Tau d is a topological space. So you see, I have named this section an example of topological space, if I am not mistaken. Yeah, like somewhat like that. So that is the example what I want to see. So basically, what is this thing? This thing is in short language, every metric space is a topological space. Topological space. So let me prove this here. We can very well do this result. I mean, I know if you have proper knowledge of metric spaces, you might have done it, but let us revisit. There is no harm. Proof. Number 1. Let us recall the definition of topological spaces. Let me verbally say it. You have already seen it in session 1. So what is a topological space? If you have a subcollection tau of 2 to the power x such that it has 3 properties. The first is the empty set and whole set should be there. So let us verify that. Clearly, phi belongs to tau d. Why it is clear, guys? I mean, you can ask me why I have written clearly. So let us, vacuous argument. So it is a vacuous argument. See, carefully see the definition of open sets. We say a set is open. I haven't said here that you should be non-empty, right? First, if for any x inside you, if you have a x inside you, then these things blah 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 should happen. But here you don't have any x inside, so what we'll say, it is vacuously true. So these kind of arguments you might have seen in your school days in 12th class in transitive relations. Like, for example, you may verify this kind of argument will come when you have a set A to be 1 to 3 and listen carefully, I am not writing this, a set A to be 1 to 3 and the relation is 1, 1, 2, 2, 3, 3. Show that this relation is transitive. So that is very important. It is again a vacuous argument. Okay, I mean, right? So it is very important to see the definition. Since there is nothing to check. So that condition is trivially true since there is no point inside the tau d thing. Okay. And x also belongs to tau d. Let us see why. Why? Because x is the whole space, right? Everything would be there. So for any x in x, take whatever radius you want. For any r bigger than 0, always this open ball centered at x with radius r is what? Contained in x. Very nice. So we are done with the first thing. Next, what we have to show? If you recall the definition topology, it is closed under finite union. So it is sufficient to do show for 2. So let say u comma v belongs to what? Tau d. What I have to show? I need to show u intersection v is also residing inside tau d. Let us see why this is happening. So what you have to show? That is to show u intersection v is open. That's what tau d was, collection of open sets, right? So to show u intersection v is open. How we show a set is open? So let x belongs to u intersection v. We should have a ball centered around x which is wholly inside u intersection v. Not inside. The better language is wholly inside, completely inside. I mean something, if two sets intersect, we can say yeah, that set is somewhat inside that because it's intersecting. But so that's why I said wholly inside, or whenever we are saying inside, we always actually mean that it is wholly inside. Okay. So let x belongs to u intersection v. So we have this. Now, this would imply x belongs to u and x belongs to v. That is by the definition of intersection, the common thing, right? And u and v. Okay. So now, what are u and v? They are in tau d, so they are open. So what it means? There will be some radius, right? Some balls containing in u and v. So there exist, say r. Now it depends upon set also. Of course the point, but the dependency of set is more important. So rv bigger than 0 such that is the way to write. I'm not just giving you logics here. My target is to also make you guys learn and understand a nearly perfect, I can say, because nothing is perfect, way to write mathematics. Such that what will happen, guys? This ball, I can avoid the suffix d because I have just metric d here. So the ball centered at x with radius ru, what contained inside u. Similarly for the other one. Now, but you need a ball which is inside u and v, right? So you see how to produce such radius. You can always imagine it in R2. So you have something like this. U, V, Oh no, sorry, they're intersecting. Let me draw it properly. Say U. Say this one is V. The whole portion. Okay, and you have some ball here. Something like this. So basically this region you are interested in. So the natural choice for this R is anything you can take, any R you can take which is less than minimum of RU and RV. Any R you can take. Why? Because see what will happen. So claim is ball centered at X with radius R is contained in, and fix it. Okay. Let R less than minimum of these things and fix it. So what is the claim? This ball will be sitting inside U intersection B. Let us see why. Now let Y belongs to BXR. What it means, guys? Distance of Y and X is less than R. Okay, good. Now, R is less than RU and also RV. So what it implies? Y belongs to both of the balls. Now, guys, this is contained in the intersection of the two. Very nice. So that's what we wanted, right? So what we have finally? We have Y in this and then finally Y in this. So we have BXR is sitting inside U intersection V. Right? We have chosen X arbitrarily in U intersection V. And we have a ball sitting inside U intersection V. Thus, U intersection V is open. Of course, in the metric space. Good. Let us proceed. I will do little bit quickly, right? The next one, because the logics are more or less same. So the third one is it should be closed under arbitrary union. Let us properly learn how to write it. So let U alpha in some arbitrary indexing family, say capital lambda, okay, in tau d. What we have to show? The union of these is open, right? Let us quickly do it, okay? So let X belongs to union U alpha in capital lambda. Now, it is in union. So it means it would be in one of them. For some alpha in capital lambda. This is a capital lambda. I know my symbols, shapes are bad. But this is capital. The lambda which is actually bigger in size, that is the smaller one. Okay, so for some alpha in capital lambda. If you are confused with this alpha and this alpha, you can change this to beta. One and the same thing. So what is this, guys? Okay, yeah, and U alpha is open. So you know what will happen. So I'm just writing it. Contained in U alpha, right? U alpha is contained in, of course, the union of all U alphas. I again said, if you are confused this alpha, you can take in place of this, say, beta also. Some beta also. The more precise way to write. But this is this accurate way. So you see, depending on x, you have a ball which is inside. Of course, it depends upon x, because x can be in any one of them. That is the dependency. So this R is, of course, dependent upon x. So what you have, guys, here, union U alpha is open, and we are done. What we have shown? We have shown collection of all open sets is a topology on X. What are the open sets? The open sets of the matrix space, how we have defined. So the conclusion, let me rewrite it. All metric spaces are topological spaces. Now, I'm gonna close this section with a definition and a note. Okay, so let us see what it is. Whenever in mathematics you have a one-sided argument, what a researcher do, he or she thinks about the converse. So the question is, are all topological spaces? Oh, sorry, no need of writing R again. Metric spaces? Let us understand this question properly. What we mean here. So what we mean here is, if you have a topological space, so let X tau be a topological space. So I should write in other words, okay? In other words. Because I am asking the same question. Does there exist a metric D, okay, on X such that tau D, what was tau D, guys? Collection of all open sets with respect to the metric D. So such that this tau D is tau. So you see, the topology tau is entirely nothing but the collection of all open sets with the metric D in this case. So is it possible? That is what the question is. Okay. So let me just give you the answer. As you guys have might guessed it, that's why I'm giving answer right now only. No, in general. Why? I'm gonna follow a very different approach, and we will be doing that thing in coming session. But let me just end this section by a definition which we can now define. So definition. Metrizable, American or British English, Z or S, okay? So don't worry about it. Metrizable spaces or topological spaces. Now, for now on, the space means topological space in the, like, whenever it is a metric space, it will be specified. So what is this? Definition. A topological space X tau is called a metrizable space. Basically, guys, it's the same thing what question I have phrased above. So if there exists a metric D such that the tau D, the topology induced by metric, I can call it, right? This is basically topology induced by metric, right? It's the topology induced by metric because it is, we are forming this by, like what I have defined above, tau D. I am following the same notation, okay? So if this is same as tau, so not all topological spaces are metrizable spaces, and we are gonna show this thing in upcoming lecture, and I want to stop here. Thank you very much for your patience and listening it. I hope these lectures will help you. Particularly, the target for these lectures are not the very smart ones who already know things. This is for the people who want to learn the subject from the scratch. That's why I'm going very slow. We will be taking things a bit faster, but not now. Let us develop some maturity. Thank you very much.